it's a pleasure to come just at the beginning of the third lecture series of our school. So David Kosower from SAGEX will talk to us about loop-level technologies. Welcome.
Thank you. So this is a set of lectures about loop corrections to scattering amplitudes. And along with the lectures that you've already been hearing from Professor Hen, and those which will start, I guess, tomorrow by Professor Dur. Bud's lecture start tomorrow?
Yes, exactly.
They're about computing scattering amplitudes, which you should think of as the kind of central objects in quantum field theory in this way of, in this approach to quantum field theory. And globally, these on-shell approaches you can also maybe think of as doing quantum field theory without the quantum fields. So we don't really need half integrals. And that, incidentally, is a quote from my longtime collaborator, Lance Dixon. And there are many applications which people are interested in, many connections to nearby fields. Of course, computing standard model backgrounds at the LHC was a primary motivation, is a motivation for a lot of things today as well. People are interested in maximal supersymmetry, in questions of ultraviolet finiteness in supergravity theories. People are starting to look at the question of using these techniques for corrections in classical gravity. There are more exotic things. How many people here have heard of the amplitudahedron? I see Nima's name. How many people have not? Okay, I guess Nima has still a few people to, Nima Arkani Ahmed still has a few people to conquer in the audience. Anyway, people are interested in finding new formulations, new principles upon which to base quantum field theory. And some of these applications, in particular the supersymmetric ones, there are many more specialized techniques. I'm going to try to focus on the techniques that are more broadly applicable. So the key ideas in on-shell methods first of all, we want to make use explicitly of information only from physical states. Physical on-shell states. In the case of gluons, for example, that would mean transverse on-shell states. That doesn't mean that there aren't virtual particles, off-shell states hiding inside tree amplitudes or hiding inside loop amplitudes. Just we're not going to use them explicitly in calculations. And the other idea is to use general properties of amplitudes in order to do calculations. So we have factorization, general property of amplitudes in quantum field theory, and that leads to the so-called on-shell or BCFW recursions, which Professor Hen has talked about in his lectures, and which I hope some of you have already started playing with. And these ideas of factorization actually apply more generally to rational functions that you might encounter in your academic career, but I'm not really going to say any more about that. We're mostly going to be focused on unitarity, which then leads to the so-called generalized unitarity method, which is what most of my lectures will be devoted to. We do have, of course, we still have the idea that things arise from an underlying path integral, even if we don't have to use it explicitly in calculation. And so that, in turn, tells us that we have to play with Feynman integrals, even if we are not going to use Feynman diagrams. And that will be the subject of Professor Doer's lectures. So there's necessarily going to be a certain amount of overlap, a little bit of overlap between the different series, and that may bore those of you who have actually already heard all this material from all the different courses before. Is there anyone like that in the audience? Come on, you guys at least should raise your hands. But by the way, actually, I was curious about one thing, which, how many people here are from European institutions? Never mind where you were born or grew up, all that. And how many people are from non-European institutions? Okay, there's a handful of people who didn't actually raise their hands either time. Maybe those are the British who are trying to stay in any event, at the risk of infringing on Professor Hen's royalties, I'll also mention there's another book by Henrietta Elgang and Yu-Tin Huang, which is also kind of a first generation of amplitudes books. And for those of you who are impecunious or particularly thrifty, there's an earlier version that's also available on the archive. And of course, I recommend them both. You should go out and buy copies of both books. So that way you won't infringe on, won't reduce Professor Hen's royalties. I should say that some of these ideas are starting to appear now in the modern generation of quantum field theory textbooks, like the second edition of Tony Z's book, and the book by Matt Schwartz. So, you've already seen the Park-Taylor amplitude a few times. I'm not going to write it down here again. And the thing that I do want to remind you is that it's an incredibly simple formula that is summarizing the results of calculating an infinite number of Feynman diagrams. And so if in a saying that I've heard attributed to Richard Feynman, a simple result should have a simple calculation, that's in sense in the last 30 years been the motivating idea to find the simplicity, find simple ways of deriving these results, and then in turn they often reveal other structure that you can then do new calculations that reveal more simplicity and that go on in kind of a very virtuous circle. So you've already seen spinor helicity, or spinors, yesterday. Just to remind you of the salient features that for the most part we're going to be focused on massless momenta. All of these techniques can actually be extended to massive momenta, but they become more complicated. If we introduce the four-vector of Pauli, generalized Pauli matrices, so the identity for the time component and the usual Pauli matrices for the space components, we can then write a matrix representation, and I won't distinguish, even though I'm distinguishing right here, the matrix from the four-vector notation just by dotting into the four matrix and into the four-vector Pauli spin matrices. And because the determinant of this matrix is the same as the Lorentz product, if it vanishes, that means that it's a rank 1 matrix. So we can write it in terms as an outer product of a spinor and its conjugate. And I'm just going to introduce a little bit more notation. We have the spinor products, of course, that are formed out of the spinors using the epsilon symbol, the two-dimensional invariant. These are two-dimensional. You can think of them as indices that are associated with SL2C, the special linear transformations, two-dimensional special linear transformations on complex numbers. The one thing that, again, I want to echo Professor Hen's warning about the sign conventions. As far as I know, the sign conventions on the angle product are universal in the literature. You have to watch out for the bracket product. It has opposite sign conventions in the QCD literature and in the supersymmetric literature. And the sign convention that I will be using is the one from the QCD literature, so that the product with the bracket product in reverse order is equal to the usual Lorentz product. There's one more bit of notation that I will be using, which is the following, basically building a vector out of a product of two different spinors, a lambda spinor and a tilde spinor. I'll often use this notation, and this just means dotting the two vectors with a sigma matrix. So one of the four vector sigma matrices and appropriate indices. So there are a number of identities that you can play with, and the two ones that are probably the most useful in actually doing calculations are the Firth identity, which in this notation would read as follows: the vector built out of I and J contracted with the vector built out of Q and R will give you the thing that you might have guessed it had to give you. It's the only real way of combining these spinors. Of course, this is a Lorentz invariant, so there's not a lot of choices. It's the main thing you have to remember is the normalization and the sign in front. So the Schouten identity in this form, again, just as a reminder, this is another thing that's very useful. I just wanted to give you a quick mnemonic for remembering the order. You're more likely to use it in this form with all the indices already contracted. So, find a bit of colored chalk here. Then you're going to go here and come back. That's going to give you the first term, IQ, and then RJ. And then the second term is going to follow the order in the original spinor products. So we've already seen the use both of real and complex momenta. If we have real momenta, then the two spinors are actually related, and they're related precisely in this way, that whether there's plus or minus depends on the sign of the energy of the corresponding momentum that you started with. And that also means that you can write a relation for the spinor products as well. It's just given in terms of the signs of the energy components of the two vectors and then the angle product. So before we can think about higher loops, we should think about one loop. And in fact, two-loop computations are still subjects of research. So if you were hoping to come away from this lecture series with your thesis topic already solved for you, then you're going to be disappointed. You are going to have to do some work on your own, but I hope I can give you most of the background. So I haven't actually said anything thus far that should be any great surprise, but while I'm erasing the blackboard, are there any questions? Okay, so we're going to start with one-loop calculations. And although we're not actually going to do anything with Feynman diagrams, they're still useful for doing Gedanken calculations. I know it's Germany, so I may not be using the word in the right German sense. I'm using it in the English sense, make believe. And we can imagine doing the calculations that way, and we want to be able to do the most general calculation with our new methods. So the thing we start with is an amplitude. It depends on all the degrees of freedom of the external momenta. In fact, on line 1, we might start by writing it, let's say, if we're going to focus on just purely gluonic amplitudes, all the external states being gluons, then they would depend on the momenta, the polarization vectors, and the color indices. And we already know that the physical states can have helicity plus or minus, but that's redundantly encoded in these polarization vectors. We know that the momenta are massless, so we can actually write these amplitudes more simply in terms of the spinor variables and the helicities and still the color. So at tree level, you really should be thinking of these amplitudes as rational functions of the spinor variables themselves, and think about them. These spinor variables are traveling over the two-dimensional complex space, actually complex projective space, but never mind that. And there's also going to be analytic content, functions like logarithms and more complicated functions that we'll see here and that Professor Dur will show you in his lectures. And there you can still think of things as being functions of the spinors, but it's often more convenient to think of them as being functions of the invariants, which in turn are then functions of the external spinors. So at tree level, we've already seen that there's a color decomposition for the amplitude, or I should say we've seen that in Professor Hen's lectures. And so let me just write that color decomposition. So it's a sum over the full set of permutations modded out by the cyclic permutations because the trace is invariant under those. So there's a trace of the SUN charge matrices, for example, if we're doing an SUN theory. And then there's a color-ordered amplitude, which is now just a function of the spinors and the helicities. It doesn't have a dependence on the color degrees of freedom. That's all encoded in the color traces. Fortunately for you, I'm going to use the same normalization that you've seen already in Professor Hen's lectures. This is incidentally not the conventional normalization in the mathematics literature, nor is it the traditional normalization in the physics literature, but it's the correct one because it avoids splattering factors of 2 and then factors of 1/2 in different places. So in a sense, this decomposition really depends only on the color Lie algebra. So it also holds off-shell. So if we imagine for a second not just computing on-shell amplitudes, but even computing some amplitudes with some of the legs off-shell so that we can sew them together in a Feynman diagrammatic kind of way of thinking, then let's imagine sewing two legs together. We're going to contract them with the color indices of the propagator, which is just a delta AB. So we now have one of these traces where we're going to contract two indices together. And so we have TA, T row 2, and TA somewhere, TA row J, and so on and so forth. So does anyone know how to evaluate this? My goodness, were you asleep when it was shown to you yesterday? Who doesn't know how to evaluate it? People are scared right now. My goodness. Well, you know, if simple questions get no volunteers, I may randomly pick someone out of the audience to answer. Yes?
If you certain traces, if you call the indices with certain traces found by the indices, freely move around and identity written down is
Exactly. So we use the SUN Fierz identity. Namely that TAIJ summed over A LM is equal to delta I M delta LJ minus delta IJ, just subtracting off the trace pieces. The easy way to remember this identity is to imagine not doing this in SUN but in UN. And then there's only this term that can arise, and it's the only possible term that can arise. It has to be a group invariant, and then you can just put in the trace subtracting thing if you're going back to SUN. So when we plug that in, we're going to get essentially two trace terms. So we're going to have things that have two traces, and that's actually going to be the generic term that we get in a color decomposition at one loop. There are some special cases. Well, one special case is where the two TAs just isolate a single charge matrix, but the charge matrices are traceless. That term will just disappear. And there are other terms when the TAs are right next to each other. And of course, we know what happens then. We will get a factor of n coming out of that. So they're so-called single trace terms because one of the traces we're able to evaluate, secretly they started out like as double trace terms. So we're going to have one class of terms which just is of the form n times a single trace, and then they're going to be genuine double trace terms. So we're in a position to write down the generalization of the tree level color decomposition to one loop. So I'm going to write down one thing which I haven't explained yet, and I'll explain it later, although I think some people can guess. I'm going to label the different classes of color traces by the index C. And then we're going to again have a sum over permutations. But now we're going to mod out by a more complicated set, not just the cyclic set. And basically it's the set of permutations which leaves the trace structure invariant. And it's going to be different for different C's. And what is the C here? The C just says that we start with row 1 and we go up to the index before C. And then we have the second trace starting with C and then running all the way to the end. And then I'm going to actually write the second line above. I know that's a little bit unconventional, reading from the bottom up instead of from the top down. I don't know of any language in which we do that, but never mind. AJ, NC, and then we just have the set of lambdas, lambda tildes, and ellipses. And again, where it's more appropriate to write things in terms of invariance, for example, the Mandelstam invariance S or T, then you should think of those here in this formula as being functions of the spinors. I'll get to your question in just a second. Again, so the dividing point between the two traces is this index C. If C is equal to 1, then this thing just collapses to a factor n, and we have what is a single trace term. Yes?
I just want to know what's the group that's modding Sn?
So what I've written here, and I apologize if it's hard to read my handwriting. I'm trying to rewrite that again. It's, I've labeled it Sn semicolon C. And what that group is, it's the set of permutations that leave the given trace structure invariant. And of course, that group is different for different traces depending on how you divide up the set of labels into the two traces. For example, if there's only one trace, then it is again the cyclic transformations. If it involves two generic traces, it'll be cyclic on either one of them. And in the special case, when you're dividing into an equal number of indices in each trace, there's also a Z2 that flips the two traces. And that's all included in this Sn:(C). So there's one other thing that I haven't mentioned, which is this sum over Nj, because of course at loop level we can have other particles circulating inside the loop, not just gluons. So we can imagine, just in the simple way, we could have scalars or we could have fermions. And yes, they could have other representations other than the adjoint. For the moment, let's just imagine that they have adjoint. They're in the adjoint representation. Otherwise, there would be changes in factors in front of here. Although these charges depend only on the external gluons. The external gluons are in the adjoint, so this particular representation holds. So that's what the J stands for. So, for example, in n=4 supersymmetric theory, you have the gluons. So for J here, let's say labeling the spin, there'd be, of course, 1 for the gluons. There'd be 4 fermions, and there'd be 3 complex scalars. So then n½ would be 4, and n0 would be 3.
Okay, maybe everyone can see the summation in C is.
Oh yeah, so it goes to.
Yes.
It's basically over all the distinct possibilities, and clearly, if you go too far in C, then if you have a very short trace here and a long trace here, you've already counted that at lower C. So you should stop basically midway. And what midway is depends on whether n is even or odd. So it's the floor of n/2. Who knows that notation? Who knows the floor notation? Okay, I won't embarrass anyone by asking who doesn't, but I did notice there were a few hands that weren't raised. You should probably learn that notation. It's not that obscure. So we have our color decomposition. And our next task is to calculate the corresponding coefficients, which again are called the color-ordered amplitudes, or the partial amplitudes, or the color-ordered sub-amplitudes. They all really stand for the same thing. And the partial amplitudes notation is a descendant of the string-based view of looking at these things. Now, it turns out that the amplitudes with C greater than 1, so the things that are in a certain sense subleading in color, are actually linear combinations of amplitudes with n equals 1 and different permutations of arguments. So leading and subleading in color here refers to the properties as you go to a large number of colors. And it's more if you imagine taking the interference between these loop amplitudes and, for example, a tree amplitude. So one of the things you have to do when you're doing that interference is you contract all the traces with a single trace. And that thing you can then simplify as some polynomial in n. And the polynomial that comes out of the single trace form for the right permutation will be a higher power of n than anything coming out of the double traces. So it'll be more leading in color. So these are, the AN1s are referred to as the leading color subamplitudes, and it turns out by taking clever linear combinations of them, you can actually construct all the subleading color amplitudes at one loop. I'm not going to prove that to you. The formulas are a little bit messy, but it's now knowledge that is close to a quarter century old, so I feel comfortable in saying just go read the original papers. So we're going to focus on calculating the leading color subamplitudes. And as I said at the beginning, we don't want to use Feynman diagrams, but we do have to use Feynman integrals. Someday we might be freed of that and be talking about different classes of integrals, but and for n equals 4 supersymmetry, one can kind of see the kernels of that already in work from the last 10 years, but for more general field theories, we're still a long ways away from that. So we're going to need to consider integrals, which undoubtedly you've seen before, things of this sort. So I'm actually going to be lazy and drop the I epsilons going forward. They're always going to be implicit. They are implicitly important, although they're not going to be explicitly important in anything we do. And it's convenient, actually, to learn how to go back and forth between this and between graphical representations. So this is just a box diagram, this particular integral, and the loop momentum is directed that way over there. Again, the convention is that all the momenta are always directed outwards. And the labels, of course, represent the momentum, so 1 here really means K1, just as in the tree level calculation. And it's a good place also to introduce a little bit of notation that I will be using throughout. So Ki dot dot j just represents the sum of momenta going cyclically clockwise around the diagram from I to j. Again, once we've gone to, especially the leading color amplitude, we have an ordering of the external legs. In fact, because it's a single trace, it's the same cyclic ordering that we have at tree level, and mercifully for you, everyone chooses the same convention, namely things go clockwise rather than counterclockwise. So we can, it'll be helpful actually to think of these integrals not necessarily with the external momenta on shell, or not necessarily with their squares being 0, as we'll see why that happens in just a few minutes. But in general, of course, I could have subtracted a mass squared from each of these propagators if the internal line had a rest mass. We're going to focus on the case that all the internal lines always are massless. So they might be gluons or they might be massless fermions. And of course, you can do much of what I'm going to say if the internal lines were massless, but it's more complicated. And I'd say there's still a lot of rough edges in the literature. So now the first thing that you may observe, so how many people observe there's something pathological about the expression I wrote down? Okay. Okay, it's a handful of people. Anyway, so the thing that's pathological about it is that I've written down this integral in 4 dimensions. In fact, it's full of divergences. This thing is actually equal to, I don't even know the sign. I guess it's probably minus infinity, actually. So it's not well defined, and the reason is that there are a lot of singularities in this integral. Singularities you're probably starting to think about are ultraviolet singularities. We know that field theory is always full of them. But in fact, this particular integral is ultraviolet finite. The singularities that we have to worry about here are infrared ones. And so what we do, as is conventional and pretty much the only way to retain your sanity when you're doing calculations in the Animus theories, is to replace that with dimensional regularization. And now, so d here, as is usual, is equal to 4 minus 2 epsilon. And for purposes of regulating infrared singularities, we want epsilon to be negative, in fact. So this thing is slightly more than 4 dimensions. And it also serves to regulate ultraviolet divergences, and it plays one more role that we'll come back and discuss later. So if we did, in the ultraviolet divergences, there are some integrals. For example, if I put some powers of the loop momentum in the numerator, then this thing will have ultraviolet divergences, and the dimensional regulator will turn them into a pole in epsilon as well. So the ultraviolet poles we know we're going to absorb into the definition of the coupling. We shouldn't be defining the coupling at arbitrarily small distance, but rather at some finite distance. When we do that, then the ultraviolet divergences will be absorbed. The infrared divergences are more subtle, and those will have to cancel when we finally calculate some physical quantity. And assuming that there's time, I will come back and talk about that in the very last lecture. So more generally, we can imagine, though, that, I mean, we have, again, we're thinking about Feynman rules. Everyone at least knows how to do these calculations in principle that way. And we want to write down some endpoint one-loop amplitude. And so we're going to draw our diagrams, and some of them are going to have, maybe just a few legs attached to the loop, and there'll be some tree that's attached to one of these legs. That's one reason for considering things where the leg attached directly to the loop is not just massless. And some of them will have all the legs attached to the loop. If you start with 3-point vertices and just build the biggest possible loop you can have out of them, then you'll have an endpoint function. And they're going to be numerators, because there's loop momentum that are going to show up in the numerator. The 3-point vertex has a loop momentum dotted into polarization vectors. Some of those polarization vectors will get contracted around the loop. Some of them will be directed outwards to external momentum. So that means that what we're going to consider in general is some endpoint, at least on line 1, is going to be some endpoint integral. So again, now I'm using this sum notation. So 1, 2, 3, and then it goes on and on and on and on and on. And finally we get to L plus Kn squared. And this thing is no longer equal to minus infinity, so let's get rid of that. I'm not interested. So what can we have in the numerator? I mean, it would be very nice if we just started with with just some constants here, but we know that there are loop momenta in the vertices. So we know there's going to be some polynomial of some rank in the numerator. And, well, let's see, we could have, for example, we could have the loop momentum dotted into external polarizations. If we have fermions outside, we could have the fermion wave functions dotted into it. We could have, if there are multiple loops, you could have the loop momenta dotted into each other. But at one loop, if we start out with L squared, that's just going to cancel something in the denominator, and we're going to get some simpler integral. We'll understand what that is in a minute. So let me not worry about that here. And of course, the loop momentum could also be dotted into external momentum. So we need to consider a polynomial that is a function of all these things. And for the moment, we're setting aside fermions, so it's really some function of L, the loop momentum dotted into the external polarization vectors or the external momenta. Now, in a Yang-Mills theory, there's one factor of the momentum in the 3-vertex. So in the Yang-Mills theory, if we build the biggest possible loop we can have, well, for an endpoint function, everything can be touching the loop. That means there's n vertices and in principle n factors of the loop momentum. So the degree of this polynomial can be as large as n. If we're thinking about quantum gravity instead, for example, then actually there's 2 powers of momentum at each vertex. And if we build the same diagram, the degree of this polynomial can now go up to 2n. So the degree depends on the theory. But as you'll see, we don't, at the end of the day, we don't actually care where we started with, because no matter how high the degree is, we're going to be able to reduce it to something simpler. So ultimately, we want to be able to evaluate all these integrals. And I suppose if you're a very minimalist, you'd be happy to even evaluate them numerically, modulo the fact that they're singularities, so you have to have some way of evaluating the poles, at least the denominators of the poles analytically. And you can imagine having a mean advisor who would send you away into a room and give you a long list of integrals and just tell you to calculate each one after the other. And some of the problems that you may be dealing with have thousands of integrals. So if you're able to you get really good and you can do some of these integrals, let's say, in a day, then you can imagine if you have, I don't know, 5,000 integrals, how long your thesis is going to last. So that's not a great idea. And in fact, in frontier problems, you very quickly realize that there's one of these hard facts of life, that analysis, like integration, is hard. But at least linear algebra is easy. So to the extent that you can, you want to reduce analysis to algebra. And it turns out that in the case of finite integrals, there's a lot you can do here. You can rewrite most of these integrals as linear combinations of simpler integrals. And in fact, you can iterate this and you get what's called a set of master integrals, in terms of which you can express all your integrals that you're interested in. And even in problems that involve thousands and thousands of integrals, you can often get down to a set of master integrals which is merely in the low hundreds, or maybe even in the dozens, or maybe even in the single digits. And then, even if you have to calculate those analytically, you won't be so upset as your thesis advisor. And that reflects the fact that there's a lot of linear relations between the different integrals. And at one loop, it's easy enough. We're going to essentially do it all in about 30 minutes. At 2 loops, there's a well-understood technology of so-called integration of parts, but there's still things that we're learning about it, and the frontiers of that could still be active research areas. Anyway, Professor Dur's lectures will teach you all about integration by parts and many other things as well. So I'm not going to say much about it. I will have to come back and say a little bit about it when I talk about two-loop unitary. But right now we're going to understand how to take a general integral and reduce it down to a simple set of integrals. Simple enough, in fact, that some of the calculations you can do on the back of an envelope, which is something that I think can be very hard with Feynman integrals. So the first goal is to find a set of integrals in terms of which we can express an arbitrary one-loop Feynman integral. And that set, this basis set, B here standing for basis or a set of master integrals, then if we take all the external momenta to be strictly four-dimensional, then that set turns out to be finite, which is maybe not something that's obvious, but it is true, and we'll see how that happens. And for some purposes, you might actually want to know if you have some target integral. And we now will show that you can write it in terms of integrals over the basis with some coefficients. You might want to know those coefficients. In general, in higher loop calculations, you will. At one loop, it's probably not that interesting to know the coefficients because at the end of the day, we'll be able to do our calculations without knowing them. But meaning that the reduction procedure is simple enough and explicit enough that we can calculate. So again, we're going to consider external momenta that are both massless and massive. The internal lines are always massless, although you can do essentially everything that I'm going to talk about for massive integrals as well. So of course we want to embark on a short journey, on a set of calculations. The first thing we need to do is equip ourselves with the right tools. And the first tool is the so-called Graham determinant. Actually, Graham, if I recall correctly, was Danish, so he's from somewhere not too far away from here. This thing, I'm going to use the symbol G. It depends on two sets of momenta, and which I'll call P and Q in the definition, and they should have the same number of them. And this thing is just a determinant of 2 times pi, the matrix built out of taking the dot products of the p's and the q's. And I should warn you again that this factor of 2 is not the conventional normalization in the literature, but it's the one that I like. So why is this thing useful? Well, if there's any linear dependence among the p's or separately among the q's, then this determinant will vanish. And if it doesn't vanish, then it's related to the volume of the hyperparallelogram that's spanned by these momenta. So far, in fact, there's nothing I've said here that limits this to 4 dimensions. We can do this in 10 dimensions, and there's a certain sense in which you can do this in non-integer number of dimensions as well. So what can we do with this Graham determinant? So imagine that we want to decompose the vectors. So the epsilons and the k's that we're starting with there, they're all, in fact, going to be, we're assuming they're all 4-dimensional, but they're not necessarily the convenient objects to have dotted into the loop momentum. So we want to write them in terms of some other set of momenta. And in 4 dimensions, we can choose four vectors. Let me call them vi here. And we can re-express an arbitrary vector in terms of those, and we can write that formula explicitly using the ground determinant. Of course, you can also solve for these coefficients explicitly. And when I write a single line, it means that both of these 2 lines here are the same. So there's just 2 copies of each other. And we can now write this as V2, V3, V4 times mu, and then C1, V4 times V2u, and then similar terms for where we replace B3 and B4 by V. So we also get, who wants to be the recorder of the exercises? Come on, this is just transcribing things. If there are no volunteers, I'm going to volunteer someone. Okay. So your job is just to keep track of what the exercises are, so if someone wants to know what they are, you can come and ask them. What's your name?
Vito.
Vito. Yeah. Okay, so he's the exercise now. Just the exercise, not the solution. The solutions you do yourself. So exercise 1 is to prove this formula. Prove this. And that's part A. And part B is generalize it to higher dimensions. So, we have some, what I might call, maybe intrinsic, not clearly intrinsic, and certainly non-intrinsic vectors that are dotted into the loop momentum. The polarization vectors don't actually appear anywhere inside the integral. And if we have a sufficient number of external momenta, in particular, well, there's momentum conservation. So if we have a 5-point amplitude, then we only have 4 independent momenta. If we have 6-point amplitude, then we have 5 independent momenta, and so on and so forth. So if we have at least 5 external momenta, then yes.
You define the ground determinant with 2 rows, meaning that you dot, yes, whatever is in the first row, the second row, but then in the formula over
yes, so maybe I didn't say that clearly enough, but when you have a single, when I write a single row, then I mean that both rows are a copy of the same row.
Okay.
So, which is because I don't write fast enough, and my hand would get tired. So. Okay, so we can choose for any integral. We can now choose a set of convenient vectors. And a convenient set of vectors would be some of the external momenta of the diagram. So we have, for example, a polarization vector. Using that formula, we re-express it in terms of 4 chosen external momenta. And now the only things we have to consider is L dot K J, where the J now are in our set of basis vectors. And this is a process, this re-expansion, that we're going to keep on doing every time we do a reduction. So imagine, unfortunately erased the loop integral itself, but imagine that we had a factor of L squared, as I mentioned earlier, in the integral. that's going to cancel one of the propagators. And then we start with L minus K1, but we just shift the loop momentum. So we just replace it by L prime. So if we have L squared, then we just replace L by L prime is equal to L minus K1. And then, of course, we have now a factor of L prime squared. The Jacobian of that transformation is just 1. So we have something that looks, again, like a Feynman integral. So let's see what we can do with this. Well, we can partial fraction, because we can write L dot Ki in the following way. We want to rewrite it as a difference of denominators and something that's independent of the loop momentum. So we can write it as follows. This is just algebra. It's a way of writing out a partial fractioning. Okay, so we have one of these factors somewhere in our polynomial, any one of it, and this is just an algebraic identity. We rewrite it in this form. What's going to happen? Well, this term, for example, is going to cancel some denominator. And so then that propagator is missing. So the only propagators we'll have then are going to be L minus K1 through I minus 2 squared. This is all, of course, in the denominator. And then the next one is going to be L minus K 1 dot I squared. So what does that correspond to? Well, that corresponds to a Feynman integral where we've pinched two of the legs together. So it's basically the same class of things, except that one of the legs now is massive. So as I said earlier, we're considering external lines massive or massive indifferently. And these terms, well, this thing is just a constant, so we could pull it out in front of the integral if we separate the integral into different terms. But notice that we've lost 1 power of L. So now it might have been that we chose one of these two legs as one of our basis vectors. If we did that for this daughter integral, as this object is called, we have to choose a new basis vector and re-expand all the things that are in our polynomial. And so we again get things in terms of a basis. These things, incidentally, and this is a little bit of language you'll hear again, because we can write them in terms of the denominators and in terms of external invariants, they are called reducible invariants or reducible Lorentz products. If there would be no way of writing them in terms of denominators and external invariants, they'd be called irreducible scalar products. So anytime we have some polynomial of some degree, we can choose basis vectors, we can rewrite all the invariants in terms of those basis vectors. Those basis vectors we can rewrite in terms of denominators and external invariants, and then we can cancel some of the denominators, or at the very least, reduce the degree of the polynomial. So when we do that, we find that our integral, we started with some high endpoint integral. It has some polynomial of order n in it. And there's some coefficient, which we can calculate here, that just comes from the last two terms. For example, that's still an endpoint integral, but we've reduced the order of the numerator by 1. And then there's going to be two daughter integrals, depending on which of the denominators is canceled. So it's a lower order. And at the same time, we've also reduced the degree of the numerator polynomial. So there's actually a sum here of a and b, sum over a and b.
Can you maybe write down a bit bigger the indices? like
Indices.
yes, having the anti-brackets is L minus K.
Over here?
Yes.
So this is 1 through I, 1 through I, and this is 1 through I minus 1. And this also is 1 through I minus 1. So, we now have, we've taken any integral that has n greater than 5 and n greater than 0. And by iterating this procedure, we get it into either integrals that have 4 or fewer external legs, or it has still more than 5 external legs, but it has no remaining numerator polynomial. Okay, so now we're going to come, so let's think a little bit about these guys are called scalar integrals, because they have nothing in the numerator, they're just constants. And let's look at a subset of these. In fact, let's look at the subset that has n greater than or equal to 6 and n equals 0. So scalar integrals with 6 or more external legs. So the simplest of these guys would be hexagon. And let's see if we can do something with them. So let's consider the following Graham determinant. We call it G1. Let's write down the following Graham determinant. So even after momentum conservation, we have 5 independent momenta. We could, let's say, eliminate momentum 6 using momentum conservation, but the rest of them are in principle independent. And let's write down the following Graham determinant. So there's 5 momenta in each of the lines. And again, the numbers just stand for, so 1 for the momenta, so 1 stands for K1, so on and so forth. So can anyone tell me what the value of this Graham determinant is? Yes. Who said that? It's right. Ah, okay, you're right. So it's 0 because these are all 4 vectors, and we're working in, because we're working in 4 dimensions, and you cannot have 5 linearly independent momenta in a 4-dimensional space, independent of whether it's Euclidean or calculus. So this thing is 0, but it's not 0 trivially. If you just expand it out, you won't see that explicitly. It's not manifested as 0. That means that we can get a useful identity if so we know the value of this integral because you put 0 in the numerator, then you get 0. So this is an identity we have. Now we can start to expand this out. We can expand out this Graham determinant explicitly. So for example, G1 you can write as L dot K5 times G1 through 4. Again, you're just writing a single line of arguments when both lines are the same, minus L dot K1, G1 through 4, 4, 5, 2 through 4, and plus a bunch of other terms. And so now, of course, we can take this L dot K5, we can partial fraction it in exactly the same way that we did earlier, and we can plug that back in. So it's clear that we're going to have some terms that now reduce to 5-point integrals. And the thing that's not obvious but turns out to be true is there's also a term coming from all those external invariants that is actually scalar. Yes, there's a question.
So over there, you are assuming the dimensional space, but does it matter that you're in dimensional reduction or like?
So and it's a great question because I haven't gone into the details. I was hoping to defer them to a later lecture. But the internal number of dimensions, so the number of dimensions for the loop momentum is d. So that, in fact, is 4 minus 2 epsilon. And really, if you want to be thinking about it concretely, it's a little bit more than 4 right now, because epsilon should be negative. But the external vectors, we're really taking to be strictly in 4 dimensions. So from that point of view, it's a little bit different than the dimensional regularization you probably learned in your quantum field theory course, where we just took everything to be d-dimensional. And that's maybe conceptually simpler, but computationally that's a nightmare, so we don't do that. But good question. So we're going to be able to expand out all these dot products, and what we're going to find is an equation of the form there's some coefficient times the scalar integral, and then there's a set of integrals where we've canceled one denominator, and there's some, actually I want to call this C0, and I. These are still scalars. We started out with a scalar integral. And the I here refers to the ith propagator being dropped. So we can, of course, this equation is easy to solve. The only thing that is not obvious is that C0 is non-zero, but I can assure you it is. We can then solve this for the scalar hexagon integral in terms of daughter integrals. And this is an exact equation. The only thing it depends on is the fact that the external momenta are in 4 dimensions. So in fact, why don't we do this exercise 2. Then work out C0 and the CI. Okay, so we're now down to 2 classes of integrals, namely n equals 5 and n equals 0, or things that are 4-point arcs. Are there any questions at this point? Yes?
Could you repeat the very last thing you did, where this G that you picked, why did you pick that G and the very
Okay, so I mean, why I picked that G is because I'm sneaky, but the utility of picking the G is I want to write down something which is 0, but in a non-trivial way. And when I have something which is 0, but in a non-trivial way, then I can get non-trivial relations between the different things that will ultimately come up. And the reason that I wrote down 5 momenta here. So the reason I'm starting at 6 point, it's the first place that I can actually write down 5 independent momenta, 5 things that are independent after using momentum conservation. And so that's why I'm starting with the 6-point integral. And I know, because I'm choosing this version of dimensional regularization, that this thing is 0 simply because all the external momenta are in 4 dimensions, and that you can't have 5 linearly independent 4 vectors. I mean, it's just, I don't know, high school algebra vector spaces, but yes.
So maybe just to recap, because this part may have been a little bit too fast.
Right.
So you pick some of the external momenta Ki to coincide with the basis vectors, the 4 one. This is what
so
the basis vectors, right?
this reduction is for general n. I wasn't actually telling you n could be 100 or 1,017 or just 17 or whatever. And I didn't actually need to pick 4 here. I could have used more. It's just convenient to pick 4 of them. And then I can reduce them using just simple algebra. This is just partial. This is basically another way of thinking about this is I take the integral, I started with some 17-point integral, for example, and I just do partial fractioning. And I can do that because I have a basis of external momenta, so I can rewrite all the factors that appear in the polynomials, all the basic monomials. And then I just partial fraction, and that partial fraction procedure stops when I get to scalar integrals. And of course, there's nothing in the numerator, I can't partial fraction anymore. Or when I get to 4 or lower point integrals. And so the next step is to show that actually, secretly, because of the 4-dimensionality of space-time, I can actually partial fraction the 6-point integrals, or 7-point integrals, or 17-point integrals, and so on and so forth. So now, actually, so the first thing that I promised, namely that the set is finite, we've already reached that goal. So the set is finite, it has the scalar pentagon and a whole bunch of lower point integrals. Okay, so the next thing is that, so we have two things we want to deal with.
There's one more question.
Sorry, yes.
I guess I have another question. I'm not sure, like, in that final result you get there, the 0 equals of these integrals.
Over here.
Yeah.
Yeah.
Where do you get, like, the I6 1 from? I see where the I5s come from, like, I just have, like, the original one,
Right.
and I always, yeah, it just, yeah, it's like,
So,
for
example, you know, L, there's going to be a term with L dot K4, for example, and that's going to involve a difference of two scalar products. Might be, for example, S45 minus S34 or something like that. And those are independent of loop momentum. And they're just a set of scalar products that you collect. And as I said, I haven't proved to you that C0 is non-zero, but that's actually what the point of the exercise is, to demonstrate that C0 is non-zero. You can see that you might potentially get some contributions to C0, right? Because there are going to be some, if I substitute that kind of equation for L5, this is a constant, and there are going to be some terms here which are constants with respect to the loop momentum, that don't involve the loop momentum. And then, of course, there's a whole bunch of them that come from all the different terms. And I haven't demonstrated to you that they don't miraculously cancel, but in fact they don't.
And then that was the argument for great sign off.
Okay. Okay, so the 5-point integral, yeah, sorry, but at least we're getting some questions in. So the 5-point integral, we need to consider another grand determinant. And this one, I'm going to choose to be, again, both of the lines and arguments are the same. So just the loop momentum and 1.4. And this is actually an interesting kind of grand determinant. It's a prototype for things that you might encounter at higher loops as well, because this grand determinant, in a certain sense, is of order epsilon. Now, there's no epsilon explicitly here. But why do I say it's in a certain sense of order epsilon? Well, imagine that I were actually taking the loop momentum to be 4-dimensional, not d-dimensional. Then I have 5 vectors inside the grand determinant. And we know that there has to be a linear relation between them, so the determinant has to vanish. So if I were taking the loop momentum from d dimensions back to 4 dimensions, this thing would vanish. So since the number of dimensions is just epsilon away from 4 dimensions, in a certain sense, this grand determinant is of order epsilon. You can certainly think of it as being of order epsilon. It's also of order epsilon in a more deeper sense, which I'm not going to have time to explain. And this, again, is something which I don't think we'll actually be able to demonstrate explicitly. It's not obvious. I stick something which is maybe of order epsilon into a divergent integral. Why don't I just get something that's maybe slightly less divergent or maybe finite? But that's actually not what happens. It turns out that if you integrate this particular grand determinant, you put that into the numerator of the integral. So again, I put in the pentagon denominator, I put G2 in the numerator. That integral turns out to be of order epsilon. It's genuinely of order epsilon. And so that means that I can now find a relation between I5 So the scalar integral, I can relate that to some coefficient times I5 of G2, plus, again, just in the same analogous way to what we had earlier, some set of coefficients, but now they're box integrals. So, if I'm willing to drop terms that are of order epsilon, and in the one-loop amplitude, something that's literally of order epsilon is not going to contribute to physical cross-section. So it's something that I'm happy to eliminate. So if I'm willing to ignore things that are of order epsilon, that says that for this purpose, I can reduce the scalar pentagon to a sum of boxes. And the way you find that is precisely the same way as we did for the 6-point integral. You have to expand this out